Good morning, everyone, and welcome to the first session of the day on distributed cryptographic protocols. Before we start, I'd like to remind you that if you have any questions during the talk, you can put them on the chat so that we can ask them to the speakers at the end of the sessions when we have a discussion round. The first talk that we're going to start is on weight-based Nakamoto-style blockchain. The talk is by Simon Holmgaard-Kamp, Bernardo Magri, Christian Matt, Jesper Buus-Nielsen, Soren Eller-Thompson, Daniel Chudi, and the talk will be given by Soren.
So, hi everybody. I'll present some work on providing a framework for analyzing variations of the Bitcoin protocol with the title Weight-Based Nakamoto-Style Blockchains. This is joint work with Simon, Bernardo, Christian, Jesper, and Daniel. So, to bring everybody on the same page and motivate our work, I thought I would start out showing how an execution of the Bitcoin protocol might look. So, in this example, we have Alice and Bob, who both maintain a block tree. And then on the right, I have abstracted the process of mining for blocks as this lottery. So initially, when the protocol begins, well, Alice and Bob only has the Genesis block in the block tree, and then they can buy some tickets for this lottery. It might be that Bob buys a few more tickets than Alice. This is no problem. The protocol is capable of handling this. So throughout the protocol, it might be that occasionally that there will be a winner. So as time goes by, it might be that Bob wins the right to extend the longest chain of the block tree with a new block B22. In this case, he will forward the protocol to Alice, who will check with the lottery that Bob in fact is a winner. And if that is the case, Alice will also append Bob's block to her block tree. So the protocol continues on, and it might be that both Alice and Bob acquire some more tickets, and eventually it can get into this unlucky situation where both parties win a block without having the time to propagate the block to the other party before they already themselves mined a block. So in this case, we will have a fork in the block tree. And this fork will not be resolved before there is some new block 1, which will now again make the longest chain unique, and which is what will determine what the longest, what the current lock of the block tree actually looks like. So let us try to get some intuition for why the Bitcoin protocol actually works. So if now I've taken the same block tree as before, and now what I've done is to plot the events, the winning events of this lottery on a timeline. So there are two observations to make. That, well, whenever there is sufficient amount of time between two blocks, then something good happens. And sufficient here means that the time between two winning events is longer than the actual network delay, which is this delta network. Then something good happens, right? But on the other hand, when the time between two winning events are less than this upper bound on the network delay, well, then something bad happens. So this leads to what I like to call the lottery dilemma. And the dilemma is all about guessing this upper bound on the network delay. So if your guess is too low, well, then the protocol will not be secure because there will be too many of these bad events where two blocks are one close to each other. But on the other hand, if your guess is too high, well, then your protocol will be slow by construction because then it will take a long time before the new block has been won. So in this work, what we do is to try to solve the lottery dilemma. And we do so by making a framework that is capable of handling variations of Bitcoin protocol. And this is what we introduce as the weighted proof of work lottery. Then I'll give you some intuitions for what security conditions for the weighted lottery applies. And finally, I'll showcase that there are actually interesting weight functions which will give a strictly better protocol than what Bitcoin currently provides. So to explain the weight lottery, I thought, well, let's just look a bit into what the Bitcoin lottery is actually about. So there, what determines if a block is valid or not is if the hash of the block is above some threshold. This is actually opposite in the real protocol, that it has to be lower than this threshold. But for the purpose of this talk, just think of it as being higher. And then, well, whenever a block is valid and is appended to a chain, well, then it has a contribution of just 1 to this chain, right? It gets 1 longer. And the rule is that the best chain, well, that is what is currently the longest chain. So the weight lottery, the weight lottery that we suggest is that everything is valid, but now we have a weight function, this W, which takes a hash and returns a value, or in this case, a weight. And then we let the best chain rule be the heaviest chain instead of the longest chain. Okay, so to make sure that we're on the same page again, well, let's just look at how Bitcoin can be instantiated as a special case of this weight lottery, right? So we just say that, well, everything is again valid. Now the weight of a block, well, that's simply just 0 if it's below this threshold from above before, and otherwise it's 1. Then it's easy to see that this longest chain corresponds actually to the heaviest chain, and therefore we actually get this Bitcoin weight lottery. All right, so let's take a look at how an execution of such a protocol might look. So again, Alice and Bob participates in the lottery, and they both maintain a block tree initially starting only with the Genesis block. Now, as every block is a winning block, the lottery's role is primarily to decide which weight each block have. It might be that both Alice and Bob starts winning 2 small blocks with the weight 0.5 each. So when they propagate, well, then there's a fork as in the other situation. The next time they buy a ticket, well, then they win again because all blocks are winning blocks. But this time, the lottery might be such that Alice gets significantly luckier and gets a very heavy block, whereas Bob still gets a light block. So this continues on, and some random blocks may appear from other participants of the protocol, and also some of the heavier random blocks might appear. And this continues on and on and on until maybe Bob, for fairness, also gets to win a heavy block. So let's look at a timeline where, again, I've plotted the events that led to the creation of this block tree. So now, even though that there's a lot of winning events, one very closely to each other, what we see is that there's still a significantly longer branch than the other. So in this case, it is only, we can observe that it is sufficient that there is enough time between the heavy block in order to form a long chain. All right, so let's think about what happens if we are given such a set of heavy blocks with sufficient time in between them, and why this actually gives us a protocol where there are no long rollbacks. So even though that we do not assume this in our proofs, well, then the goal of such an adversary in order to create long rollbacks, well, that would be to create 2 equally long chains. And this means that you need to fill in these blanks. Well, naturally, it's a bit easier for the adversary if the set of heavy blocks are only distributed across 2 different chains. Well, then what we observe is that if there is sufficient time in between the creation of these heavy blocks, well, then they will have a different placement in the tree. That is, that their weight range cannot overlap. All right, so it might be that the adversary gets a bit of help from these light blocks, which appears very rapidly and does not have time to propagate before the heavy blocks are being created. But still, the adversary needs to create more or less half as much weight himself as there are heavy blocks in order to provide a rollback. So this is illustrated here with these red blocks. All right, so now let's think about what our definitions of such a heavy block should be. So now we have just plotted so we have the hash domain on the x-axis, and then we have sort of a total weight 1 at each value on the y-axis. Now let's just take an arbitrary threshold to determine, well, we say everything above this h, that is heavy, and everything below that h, that is light. And what we notice that, well, this area A, there's a small waste here, right? So that even though that we define our notion of heavy blocks somewhat correctly, well, then might be that there are by pure chance, very small chance that there are some blocks in the area A which should result in a good event that does not. So we gray out the small area. Then there's the area B, which is all the weight 1 by light blocks. What we want is that this area A, well, that should be significantly larger than this area B. Let's think about what happens when the network delay is increased. Well, so when the network delay is increased, then this grayed out area of blocks that were 1 too close to each other, well, that now becomes larger, which means that there will be less weight in the area A that outweighs the area B. So this is sort of bad for us. Now let's think of what happens if we move H to the left instead. Well, then we will also get this case that there are too many overlapping heavy blocks. But on the other hand, if the network delay actually decreases, well, then the area of waste actually decreases. And now A becomes significantly larger, even with a smaller H. So let's try to use this to create, to think about how a nice weight function looks like. So, well, one suggestion might be to have an exponentially growing weight function, just as the one plotted here. Well, then there will surely be a larger amount of weight, 1 far to the right than to the left. This does unfortunately not work, as this gives us that the adversary can just by with a bit of luck be very lucky and win a huge block which outweighs all of the honest blocks. So this will give us a very bad confirmation time. So one way to counter this is to try to cap the variance of the weight function, such that the adversary does not have a chance to win 2 heavy blocks. So one suggestion which looks pretty so what do we require? Well, we require that there is low variance, such that the adversary cannot be super lucky and win a very heavy block compared to what the honest parties have won. And then we require that these 2 areas, that A, the sort of the beneficial area, should be way larger than this area B, which is sort of the unproductive area. Okay, so one suggestion, which I guess we all know, which have this property, well, that is Bitcoin. Well, it has low variance. The adversary cannot be super lucky compared to all of the other blocks, right? Because there is only one weight, namely 1. And it also has this area property A, that A is way larger than B if this threshold is set correctly. So this means that it, in the worst case, under attack is actually secure. But in the best case, we had this problem that we ran into the lottery dilemma, right? That it is no, if the upper bound of the network delay gets too high, well, then it will be slow forever. So another suggestion could look like this, which we call the capped exponential function. So again, this is a function which has a fixed threshold, and from there on we cap it to achieve this low variance property. But until then, we let it rise exponentially. So again, low variance, and the area A is way larger than the area B. This means that in the worst case under attack, this is actually secure. But in the best case, however, when we are not under attack, this thing has an additional property. It is super fast. All right, let me try to illustrate why this choice of weight function actually provides a speed up when there are no adversaries. So this was the situation that we wanted to argue did not happen, but only in the case that there were no adversary. So let's just remove the red blocks. So, well, if there are no red blocks, then all of the heavy blocks, they will surely be on the same branch. But now again, if the network is actually faster than what we guessed it was, well, then the light block, which was the light blocks before, well, they will also have time to propagate. And it will only be these super, super light blocks that you see on the right, which do not have time to propagate. So this means that the definition of what heavy is kind of readjusts itself. And now we can essentially get the guarantee that there only needs to be a very few light blocks in order to outgrow the very light blocks. All right, to sum up, in this talk, I have presented a generalized best chain rule that assigns different weights to each block. I hope to have given some intuition for how to reason about security given sufficient heavy blocks. I hope to have given some intuition for what properties a good weight function should satisfy. And then I have presented a weight function which achieves a speed up under certain optimistic conditions. In the paper, you can find a framework for analyzing all kinds of different weight functions. This includes general proofs for chain growth, chain quality, and common prefix. And it includes precise guarantees for the class of capped exponential weight functions, which furthermore, which gives this weak kind of form of optimistic responsiveness in the sense that it speeds up in the actual network delay if there are no adversarial behavior at the time. Thank you for your attention.
Okay, thank you, Soren. Thanks for the talk. Now we go for the second talk. I remind again everyone that if you have any questions, please put them in the chat so we can ask them during the question and answer phase later. So the second talk is Law of Appearing by Diego Araña, Elena Pagnin, and Francisco Rodriguez Enriquez. And Elena will be giving the talk.
Hi everyone, I'm Elena Pagnin and I'm here to present Law of Appearing. This is a paper appearing at LatinCrypt 2021. Law of Appearing is a joint work with Diego Araña and Francisco Rodriguez Enriquez. Let me begin by introducing you to what a pairing is. A pairing is a mathematical map. It takes as input 2 points, A and B, A from a group G1 and B from another group G2, and it returns another point, EAB, in a target group GT. Usually these groups are elliptic curve groups, and you might recognize it from the shape of these diagrams below. This doesn't say much about a pairing. What actually makes pairing interesting is 3 mere properties. First of all, they should be efficiently computable, which means the algorithms that we use to implement them should run in polynomial time. Second, it should be non-degenerate, which means that when we do a pairing of 2 points that are not the identity points in the group G1 and G2, we get a point on GT which is not the identity point. And finally, we have the most interesting property, which is bilinearity. This property is represented by the red arrows in the graph below. Bilinearity essentially states that given a multiple of P and a multiple of Q, the pairing of these multiples is actually a multiple of the pairing of P and Q. Now that we know what a pairing is, let's see what we can do with pairings. And the answer is essentially anything: coffee, mate, or identity-based encryption, aggregate and verifiably encrypted signatures, short signatures, non-interactive argument, verifiable delay function, you name it. Pairings have shown to be a very versatile tool in cryptography, and they have been used to realize essentially any cryptographic primitive. So this is of course a good property of pairings. You can do fancy crypto, fairly lightweight with it. The bad is indeed this efficiently computable property that we said. This is true only for servers or computationally powerful devices, but it doesn't always hold for resource-constrained devices that, for instance, suffer of very limited memory and therefore they cannot store all of the libraries needed in order to compute a pairing. Or simply because we have too weak computational power. Another weakness of pairings is that they are not post-quantum secure, meaning that if our adversary would have to use a quantum computer, then the security property that build around elliptic curves and pairings won't hold anymore. The pretty side of this, though, is that we can at least get rid of the efficiency computable problem by outsourcing the pairing. And this is precisely what our love protocol does. For those of you who are not familiar with the outsourcing computation, let me tell you very quickly how the model works. We will have a client and a server. The client has a computation that wants to compute this F on input X and wants to compute the output Y. The whole idea around outsourcing computation is precisely what the word says. We want to move the task of computing the function F from the client to a computationally powerful server. The naive way to do so is simply that the client will send the input X to the server and the server will reply with the output Y. This works wonders so long we are in a perfect world where the server is not malicious. But if we have a server that misbehaves, there is no way for the client to check this. So what usually happens is that the client will send, together with the input X, also some auxiliary material, which might depend on the function to be computed F and on the input X itself. And the server will return not just a value Y, but also some auxiliary material that essentially explains why the server claims that the value Y is indeed the output of F when computed on the input X. There are three main properties that protocols for outsourcing computation should satisfy. The first one is correctness, which essentially states that whenever the server behaves honestly and indeed returns Y that is f of x, the client will accept this Y. Then we have efficiency, which is the core of outsourcing computation. This property states that the computational cost on the client while running this outsourcing computation protocol should be less than the cost of computing F itself. Otherwise, why are we outsourcing at all? And finally, we want to have security. Security states that the client will never accept a value Y, which is not the legitimate output F of X. Or at least it accepts wrong values only with negligible probability. And negligible means so small that it never happens. There is also a set of additional properties that one might add to the wish list. The first one is to allow for more interaction, or we can have input privacy, which essentially states that we are encoding the input X so that the server will not learn it. Output privacy, on the other hand, says that the server will output an encoding of the output Y, so the server will never learn the value it has computed. And of course, we can also have function privacy, where the server doesn't even know what function it's computing. In this work, our love protocol only satisfies the main properties. We have looked a little bit into providing input privacy, and I will come back to that towards the end of the talk. Good, then now we are finally ready to spell out the meaning of the title of this work. Love appearing stands for lowering the costs of outsourcing and verifying efficiently a pairing computation. We are not the first to tackle the problem of securely and efficiently outsourcing a pairing. Actually, there is a fairly long history of problematic solutions. Here I list only a few. The reason why these are problematic is that, despite what the title claims, usually there are some issues. For instance, we might have a secure delegation, but this is not efficient, like the cost of the whole protocol between client and server becomes heavier than the computational cost of computing the pairing itself. Or we can have efficient protocols, but these are not secure against malicious servers. Other times, the efficiency claims are true only for certain specific parameters or certain curves only. This was true until last year, when Differential-ML et al. Published a paper with title Secure and Efficient Delegation of Pairings with Online Inputs. So we love this paper, we read it, and we wanted to probe their efficiency claim. The main motivation behind our skepticism is that Differential-ML et al.'s paper contains theoretical estimates that are extrapolated from old benchmarkings dated 2013 from the paper by Boss, Costello, Nering, exponentiating in a pairing group. And while implementing Differential-ML et al.'s protocol, we actually found out that the efficiency estimates they give are inaccurate. And on top of that, they also were discarding some heavy subroutine needed in order to provide security. For instance, this was membership testing in GT. That was quite a disappointment, but it also gave us the sprint to try to improve it. And that's how we came up with our LOVE. LOVE is an improvement of Differential-ML et al.'s proposal. LOVE is the most efficient protocol to date for securely outsourcing the computation of a pairing with online inputs. I will explain what it means in a sec. And the protocol is provably secure even against a malicious server. We also provide the first implementation of a secure and efficient protocol in this offline-online setting. In addition, we perform an in-depth analysis of our LOVE using different parameters, and along the way we also provide new benchmarkings that update the old estimates by Costello et al. That we mentioned before, and can be considered as a result of independent interest. Next, I will introduce the offline-online paradigm for delegation of a pairing. The idea in itself is very simple. It's a tiny tweak to the outsourcing computation framework that I explained before. Here we separate an offline phase that is run by the client. What is crucial about this phase is that it is independent from the input to the computation. The online phase instead can happen anytime after the offline phase. Intuitively, this corresponds to the moment in which the client gets to know the pairing arguments, A and B, and therefore starts the interactive protocol with the server. Again, we will have three main properties. In this case, correctness states that whatever the client outputs at the end of the interaction with the server should be indeed the pairing of A and B. Efficiency, consider the cost on the client only during the online phase, and this should be less than computing the pairing. This is motivated by the fact that the offline phase can be run at any point in time, possibly when the client has access to an electricity supply or maybe a trusted server, while the online phase is on demand and should be very fast. For security, we again demand that the client should output an incorrect value only with little probability. This probability is negligible in lambda, where lambda states the computational security parameter. This is connected to the size of the elliptic curve groups that we consider. In addition, the probability should be smaller than 2 to the minus sigma, where sigma is the statistical security parameter of the schema. The fact of having two distinct security parameters is something that our LOVE protocol inherits from the Differential-ML et al.'s protocol. Essentially, lambda, the computational security parameter, sets the size of the groups we are working with in order for us to trust the security of elliptical cryptography and pairings, while sigma, the statistical security parameter, is the one that is setting the accuracy level of our protocol for actually outsourcing the computation. So sigma is connecting directly to the probability of catching a cheating server. Now we are ready to see how our LOVE protocol works. Here are the four main algorithms of the LOVE protocol. We have an offline setup, which is connected to the offline phase. And then in the online phase, we will have an online setup, a compute, and an online verification. Three of these algorithms are run by the client, while the compute algorithm is the only one run by the server. LOVE is very similar to the Differential-ML et al. Scheme, but we did two minor yet very interesting tricks, and these are highlighted with a frame in the slide. The first one is on the compute algorithm on line 5. Here, the original protocol by Differential-ML et al. Was actually computing the pairings gamma 0, gamma 1, gamma 2, and returning these three GT values in the out string. Instead, we notice that there is no point in giving 3 values. We can intuitively merge the pairings gamma 1 and gamma 2 into one GT element gamma prime. This has the benefit that now in line 5, we can share the computation of the exponentiation of the 2 pairings, and therefore makes compute more efficient. And second, the length of our out string, output by the compute algorithm, is 1/3 shorter compared to Decrescence et al.'s work. The second change we did is on the onVerify. First of all, because we are having one less group element to check, we will only need to do one membership testing. This is line 2, and not a second one, which is the case for Decrescence et al. Actually, as I mentioned before, this GT membership testing was something that was discarded into the efficiency estimates of Decrescence et al.'s work, and we instead showed that this is a fairly heavy computation. The main change, though, on the onVerify comes in line 3, where we do a slightly different equality or inequality check. Since in love we have one less gamma to play with, it's going to just be gamma prime. We are checking if gamma prime satisfies a specific combination between gamma 0, which is the pairing that we ask to outsource, and gamma, which is something that the client keeps a secret, and it has been computed on line 4 of the offline setup. First of all, let's look at correctness. We see that if the server is behaving correctly and therefore computes gamma 0 and gamma prime as he's been asked to, the client will output to gamma 0, and gamma 0 is exactly the pairing between A and B, so correctness is easily satisfied. Diego will discuss the efficiency in the next slide, so let's move towards security. I do not have the time to go into details, but I'll try just to give an intuition. First of all, we will focus on what happens on line 2 of the offline setup. Here you can see that we sample a challenge value C from a set of size 2 to the sigma, therefore exponential in our statistical security parameter. And we also sample a randomness R from the set of, let's call them exponents of the groups. Now this randomness R is embedded into 2 different points, V1 and V2, and in V2 we embedded the inverse of R. So it's not hard to believe that if I combine with V1 and V2 in an appropriate way, we will be able to remove the contribution of R, while the challenge C is embedded only in the point W2, generated on line 3 of the online setup. So the core of the security proof is that the server doesn't know the challenge C, and even if it was able to combine things together in order to remove the contribution of R, it will still need to guess the correct C in order to produce 2 values, gamma 0 and gamma prime, that satisfy the probabilistic correctness check that is run on line 3 of the onVerify algorithm. The proof is actually a bit more complicated because we want to prove that whatever tuple we're sending in the public output of the online setup, stated on line 4 of onSetup. So we want to prove that this tuple leaks no information about this C. Therefore, the only chance the server has in order to fool the client to accept a wrong value gamma 0 is to guess the correct C. There is only one C that will satisfy the probabilistic check. I know it's a little bit hand-wavy. If you want to have more details, I encourage you to read the proof that you can find in the paper. Now the mic passes to Diego.
For our experimental evaluation, we have implemented LOV and the protocol by Decrescence et al. As related work. These were implemented using the Relic library, and the code is already available in the corresponding repository on GitHub. We benchmarked group operations in all pairing groups, G1, G2, and GT, such as the scalar multiplications and exponentiations, using both full-length exponents and shorter ones to capture the different situations that arise in the protocols. We also benchmarked the cost of computing a pairing locally to serve as a baseline. Timings were taken as the average of 10,000 executions on an Intel Skylake machine. All the numbers for this set of benchmarks can be found in the paper. We omit them here to save some time, but they could be interesting for your own protocol if you are implementing some pairing-based cryptography. For membership testing in GT in particular, we have implemented 2 different choices, a more conservative and a more efficient approach, and picked the faster one. The experiments include multiple choices of parameters at different security levels, but always consider 50 bits of statistical security. We picked the legacy BN254 curve at approximately around 100 bits of security, and a larger curve adjusted for the 128-bit security level. We picked two BLS12 curves at around 128 bits of security. The first one is the widely adopted curve over a 381-bit prime, and the second one is a GT-strong curve over a slightly larger prime. And the idea behind this is to be able to estimate the impact of membership testing in the execution of these protocols. Finally, we picked the BLS24 curve at the 192 security level for illustrating the performance of the protocol at higher security. In the first graph, you can see the timings for pairing delegation with public inputs. The y-axis has the latency in thousands of cycles in log scale, such that the numbers are closer and easier to compare. The x-axis has the different choices of parameters for all the curves we implement here. The red label corresponds to the baseline for local computation. The shades of yellow have the timings for client-side computation in both the LOAF protocol and related work. The green bars have the timings for pre-computation, and the blue bars have the cost for the server-side part of the computation. The lighter shades always correspond to the LOAF implementation across the different curves. We can see that for the BN254 curve, the related work protocol is actually slower than performing the computation locally. LOAF is able to improve that such that a speed up of 16% is obtained. For the other curves, both protocols present a speed up over the local computation, as you can see here, with LOAF increasing the speed up due to the savings in membership testing. The highest speed ups for both protocols are for the GT-strong curve, where they reach above 50%, since no membership testing is required. For the server-side timings, LOAF improves the latency by 20 to 25%. A recurring trend here is that the cost of offline computation is quite high, as you can see by comparing the green bars to the yellow ones, since a pairing and additional group operations need to be performed on the client side. In the next graph, we can see timings for pairing delegation with private inputs. In this particular case, the protocols are not more efficient than local computation, as we can see by comparing the yellow bars to the red ones, except by a very minor speed up in the BLS24 curve, which is exactly this one here. The pre-computation cost is still quite high, and LOAF provides some saving for both client and server, although not sufficient to be useful in practice.
Thank you, Diego. To conclude, let's look at the takeaways from this talk. First of all, we love that finally we can delegate a pairing in a secure and efficient way. Yay! Second, we encourage the community to use proof of concept implementation in order to back any efficiency claim, not just theoretical extrapolation, and especially not extrapolations that are based on all the benchmarkings and disregard subroutines in the algorithms. Let's look into the futures. What are some implications of our LOAF protocol and future directions that we can take from there? First of all, we talked a lot about GT membership testing. An improvement on this regard will also make our LOAF more efficient. Secondly, one could use LOAF to create more efficient verification in pairing-based cryptographic primitives that have a designated verifier. In this case, since we know the designated verifier in advance, we can actually, let's say, encrypt the challenges C and R, the points U1 and U2 that we utilized in our LOAF protocol, encrypt them for the designated verifier, who can then enjoy an even more efficient verification of whatever cryptographic primitive we have at hand. For future direction, it's totally interesting to see how we can make LOAF with privacy. That would be, we create input privacy and maybe also output privacy. Our first tests show that it's hard to get this in an efficient way. Maybe there are some smart tricks that people can do to achieve efficiency and a higher level of privacy for the clients. And finally, we're also considering to move LOAF into Amore. That would be basically considering amortized efficiency. So we have seen that the offline setup at the moment needs to compute a pairing and it's not so efficient, but what if we can use whatever we compute in the offline setup to actually efficiently verify a series of pairings? This is still a work in progress. We have now reached the end of the talk. I thank you for your attention. I hope you liked the talk and that I got you a little bit excited into this lovely line of work.
Okay, thank you, Elena. Thanks for the good talk. Now we go for the final talk of our session, which is implementing secure reporting of sexual misconduct, revisiting Who2, by Alexandro Hevia and Ilana Mergudishtal. And Ilana is going to give the talk.
Good morning, I am Ilana Mergudich, and today I'm going to present the work that we did together with Alejandro Hevia about implementing secure reporting of sexual misconduct, specifically revisiting Who2. So I'm going to start with a little bit of a story of how we came up with this work, and then I'm going to describe what we did and how we did it. So we start with a very concerning context in which almost 40% of students of one of Chile's biggest universities say that they have been victims of sexual misconduct, and 65% of them did not report it. Similar statistics can be found for universities all over the world. On the other hand, Project Callisto showed that 90% of sexual assault episodes occur by repeat offenders, and that people are more willing to report sexual assault if they know that other victims of the same perpetrator exist. So with all of these ideas in mind, it makes sense to design a protocol in which the identities of the accusers and the accused are hidden, are private, until a certain number of people accuse the same perpetrator. In order to implement this, we set a number that we will call quorum, which is the minimum number of accusations that actually need to be submitted so that the identities are revealed. Let's see an example for quorum 3. So we would have a first accusation and a second accusation, and we would not know the identities of any of the people involved. And once the third accusation comes in, then the identities are revealed to the corresponding authority. So the first protocol to use this idea, to propose this idea of the quorum and to actually implement it, was the Callisto project. And they actually implemented it in a few universities with very good results. People are the amount of people that report actually grew, so the idea of the quorum works. However, it may have some security issues that were described by Who2. And Who2 was the second protocol that was designed with this idea of the quorum in mind, and it was proposed with stronger security guarantees, and is the main subject of study of this work. There's a third protocol called the Secure Allegations Escrow that also takes this idea of the quorum. However, it may reveal more information than one should be revealed before the quorum is reached, but it has some very interesting tools that we actually used in our version that we call Who2+, which is an improvement of Who2. So what we wanted to do was to implement a secure and efficient sexual assault reporting system, and we found Who2, we found it very interesting, we were satisfied with its security guarantees, and started to look into it and study it to see how we could implement it. And quite surprisingly, we found two gaps, two operations that were left unclear. The first one could compromise the anonymity of the accused. We showed the attack of how this could be done in the paper, but fortunately a straightforward fix solved the issue. It required a new proof, but it was also pretty straightforward. But the second issue was more complicated because it was something that was left unclear and it was not obvious how to implement it. And the straightforward way to do it would compromise either the anonymity of the accuser or the accused. And instead of trying to fix it and see how we could make it work with those same tools, we decided to take a step back, to re-examine the entire phase where this problem was arising and think of an alternative for that entire process. And we came up with an alternative that was much more efficient. So this motivated the third and most important contribution of our work, which are two improvements in efficiency in two specific components by changing the cryptographic tools used in those components. So later we will explain exactly how we did that. I'm going to quickly run through some building blocks and notations so that it will be easier to understand what comes next. First, we have Algoma encryption. So we use both C and E for Algoma encryptions, well, and encodings, but well, when you see that, we are always referring to Algoma encryptions. And also we really strongly rely on threshold cryptography, where we have an amount of servers and we need a majority of them to cooperate in order to reveal any private values, in order to decrypt some messages or to compute some operations. We use the notation of the brackets like this. So anytime you see that, that means that a value is secret shared among the servers, and we operate over those shares using the notation that you can see here. And the last one are distributed input pseudo-random functions which work just as normal PRFs, but the secret key and the input are secrets shared among the servers. So before explaining how we fix these gaps or what exactly we did to improve efficiency, I will explain how the original Who2 protocol works so that it will be clear what was our starting point and what was it that we built over that. We will separate this into 4 phases: initialization, submission, verification, and matching. So during initialization, the servers compute some keys that they send to each user. Here we see one user, but they do this for every user in the system. So they send the user a public key R and a private key alpha. Alpha is secret shared among the servers, so they don't know it, but the user receives all the shares and can reconstruct it. And the public key R will be used as the identity of the user, and these users are the potential accusers of the system. So from now on, we will identify all accusers with a value R, an identity R. So now if user R wants to submit an accusation against someone with identity D, the first thing that it has to do is to create an image of D that we will call S. This is just to have it in the domain that we need, but the important thing here is that both D and S will represent the identity of the accused, while R, as I said before, will represent the identity of the accuser. So the user needs to send Algoma encryptions of D, R, and S out of the identities, and a value pi that here represents several proofs of knowledge and signatures of knowledge that the servers will later verify to see that the accusation is not malformed. And the user also needs to provide a secret sharing of S, of the identity of the person that it is accusing. So then the servers receive this accusation, they verify all of these proofs, all of these signatures, and then they need to check that the accusation is not duplicated. This is important because here is where the second gap arises and where we make our first efficiency improvement. So what we want to do is to make sure that there are no previous accusations with the same accuser and accused, so the same R and the same S. So what Who2 does is it proposes an equals operation in which all servers can cooperate in order to determine if 2 Algoma ciphertexts encrypt the same value. So what they do is that the servers take the new accusation and they cooperate to compare it to every single accusation that is already in the system. This is not very efficient because it requires many distributed operations, because it requires a distributed operation for every single accusation. So as the number of accusations in the system grows, this becomes increasingly inefficient. Then in the matching phase, first the servers check if the quorum has been reached. And if it has been reached, they need to find all of the accusations that need to be revealed. So they know which is the accusation that triggered the quorum, but they need to find all the other ones. And they do it in a very similar way to how they did the duplicate revision. They use this equals operation in which the servers cooperate to compare this value to every other value in the system to check if they are the same or not. As you can see, this is very, very similar to the duplicate revision. And this is how we thought about improving the efficiency of this component too, because we found that gap in the duplicate revision, so we had to re-examine that phase. We found a way to make it more efficient, and then we saw this that was so similar that we figured there must be a way to make this more efficient too. And even though the fix that we did for the duplicate revision does not work for these two, we were able to come up with a different alternative to make this more efficient too. So now I'm going to go a little bit into these first 2 gaps, or unexpected surprises that ended up being very inspiring. They inspired all of this work. So the first one occurred when the servers had to check if the quorum has been reached. So what Who2 does is it uses privacy-preserving polynomials to check this, but it was not clear how to use them securely. So we figured out that using an extra step of randomization could fix the issue and required a pretty straightforward proof, as I said before. But the second gap was a bit more complicated because it was a procedure that was not clear. Let's go back to the duplicate revision so that you can understand it. So as I said before, Who2 proposes this equals operation that lets you compare Algoma ciphertext. But in this case, we don't have to compare 2 Algoma ciphertext, but we need to compare 4 of them. So it was not clear how to do this. The straightforward way would compromise the anonymity of the accuser or the accused if we compared one first and the other one second. And perhaps we could come up with a way to do it, maybe doing a randomized linear combination of the values or something like that. But it was already not clear. And as I mentioned, it was not very efficient because it required so many distributed operations that we decided that instead of just coming up with a small fix, that we could come up with a more efficient alternative. So what we did was we used the distributed input PRF inspired by the secure allegations escrow. So what we do is we define the value tau, that is an image of R. So now tau and R will both be used to identify the accuser. And remember that both S and D identified the accused. So what we will do is we will produce a combined input of S and tau, the identities of the accused and the accuser, and calculate a PRF over this value. So in this way, we will produce a value P that is indistinguishable from a random value. So it reveals nothing about any of the identities, but it is related to them. So if another accusation were to have the same S and the same tau, then it would have the same P, and this could be seen by the servers. So what we will do is that now the servers, when they have to do the duplicate revision, instead of doing what they did before, they will now use their shares of S and their shares of tau, which will be sent during submission. Now, when the user submits an accusation, it also sends shares of tau. So the servers will have these shares. They will use them to calculate this distributed input PRF, and they will obtain a value that is public and that they all know and that reveals nothing about these identities. And what they can do now is that they can locally go and compare that value to every other value calculated before, but they don't need to cooperate anymore to do all of these comparisons. They can just locally do it. So we replace several distributed operations by a constant amount. We do one calculation, which is this distributed input PRF, and this unlocks all the information that we need, and now each server can just go and do it. So by doing this, we realized that distributed comparisons could be done in a much more efficient way. We did not really need to have distributed operations for every single comparison, and we like this idea of having one operation that unlocked everything else. So going back to the matching accusations process, remember that we had the accusation that had triggered the quorum, and that what Who2 does is it compares that encrypted value to every other encrypted value in the system using where the servers need to cooperate for each of these comparisons. So we figured out that maybe we could find a way to do something similar to what we just did for the duplicate revision. So we would like something like this, some way that the servers could cooperate once, produce a public value, and with that public value, they could just, each server could just locally go and check which are the matching accusations. So in order to do this, we found a way to do it, and I will first explain a naive approach that will help understand how we build our solution. So imagine we could have a public key and a secret key for every possible S, for every possible identity that could be accused. And this public key would be, well, public, and the secret key would be distributed secret shared among the servers. So what a user could do is that when it wants to submit an accusation against an identity S, it would encrypt something, anything, a 0, a 1, it doesn't really matter. But the important thing is that it encrypts it with the public key for that identity S. So then, once the quorum is reached for an identity S, and now this identity is public, because when the quorum is reached, the servers know which is the identity that is revealed, that is the accused, the person that is accused, they could reconstruct the secret key for that identity, and they could maybe make it public at that point. And so now each server could use this secret key and locally try and decrypt the values that were sent during the previous submissions in the system. So we have this idea again of having one distributed operation that in this case would be reconstructing the secret key for a specific identity, and that would produce a public value that would allow the servers to locally get all the rest of the information that they need. This obviously has some pretty big problems. The first one is that computing keys for every possible identity is not efficient at all. And because we would hopefully imagine that most identities will not be receiving accusations, so this is not very efficient. And the second one is that we have to be really careful about not revealing any information about the accusations that do not match. So that when we try to go and decrypt a certain value with a secret key, if the secret key does not match, we should not learn anything about that value that could not be decrypted. So what we will use is a variant of identity-based encryption, because identity-based encryption solves our first problem, because it allows us to build the keys as we need them. So we have public parameters and we have a master secret key, and with the public parameters, we can encrypt for a certain identity. And with the master secret key, we can produce the secret key for a specific identity as we need it. So it allows us to create these keys only when we need them, and we don't need to create all of these keys beforehand that we will probably not use. So the variant that we proposed is a distributed IBE, where the master secret key is shared among the servers. So instead of having a secret key for every single user shared among the servers, we have this one master secret key, and the servers can cooperate and use just this key to produce any secret key for any identity when they need it. And also the identity for at the moment of encrypting would also be a secret shared among the servers, because it will not be the user that makes the encryption, but the servers will be doing it. I will explain that better in a minute. And the second thing that we do is we add strong robustness that solves our second issue and ensures that if a server tries to decrypt a ciphertext that is not intended for a specific identity with a secret key that does not match, it will learn nothing about it. So to do this, we apply the transfer by Abdallah, Velare, and Neven. So we use as a base the variant of the IB scheme by Gentry, a variant proposed by Ocano and other authors. And we apply this transform to it, which requires a commitment that we also have calculate in a distributed manner. What is very interesting is that we realized we didn't really need a message. I also said that in the naive approach when I was explaining that we could encrypt a 0, a 1, it doesn't really matter. So we realized that we could actually simplify the scheme that we were using as a basis. And it is very nice because it is a very simple solution that works because no message is being encrypted. The only thing that matters is the identity that it is intended for. So how is our protocol looking now? Now, during initialization, the servers will generate a shared master secret key, and they will produce all the public parameters needed for IB. Then, during submission, the servers will receive the shares of S that they received because everything else works as I explained before, and they will use these shares to encrypt for that identity S, and they will save this value. That can be public because it's an encryption, so it reveals nothing about S. And then once the quorum has been reached and the servers need to know which are the accusations against that identity S, the S at this point is public. They all know it because it has been revealed. So now they use their shares of the master secret key to generate the secret key for that identity S. And now each of the servers can go and locally try and decrypt all of the values that were produced during previous submissions and check if the accusation matches or not. So in a very similar way to what happened with the duplicate revision, we now have just one operation in which the servers need to go, one operation in which the servers need to cooperate. And once they do that, they can just go locally and make all of the comparisons on their own. So now we have this short lemma that sadly we do not have time to show you the entire proof, but I can give you a little bit of the reasoning behind it. So what it tells us is that this distributed IBE that we proposed is actually CPA secure in the context of IBE, and that it is also strongly robust. This follows from the fact that the transform proposed by Abdallah, Velare, and Neven tells us that if we have an CPA secure IBE scheme and we add a hiding and binding commitment in a specific way, then we will obtain a scheme that is CPA secure and also strongly robust. So the IBE scheme that we used was CPA secure, and the commitment that we used was about hiding and it's about binding. And it was hiding because, as I mentioned, it is calculated in a distributed way by the servers. So that gives it the hiding property, and that achieves what we need. And the last thing that is missing here is to see that the distributed IBE is actually also CPA secure. But this follows from the fact from the correctness and secrecy properties of secret sharing. So we can simulate it and go from the normal version to the distributed version and still have CPA security. It is interesting that we only need CPA security and not CCA. And this is because the servers are the ones that are going to make all of the encryptions, not the users. So we only require this. So with all of these changes, we now have our finished Who2+ protocol, and we have this very important theorem that tells us that it can be simulated. Sadly, we do not have time to show it here, and due to space constraints, we could not give the entire proof in the paper, but the proof is in the extended version that it can be found on ePrint. So now, seeing more in terms of efficiency, we can see that the number of distributed operations, the online distributed operations, were reduced from a linear amount over the number of accusations in the system to a constant amount. This does mean that the number of offline operations grows, but this only means that initialization will be slower, but once that is done, submitting new accusations is much, much faster. It is important to note that this protocol is still a linear protocol because the process of finding if the quorum has been reached still requires a number of distributed operations that depends on the number of accusations in the system. But in these two components, the duplicate revision, that is DR here, and the matching accusations, MA, we did reduce it from a linear amount to a constant amount, and that is a significant improvement. And in practice, we can also see this improvement. You can see that the yellow and pink lines represent Hu2+, and the blue and green ones, the original Hu2. And in the case that the accusation does not reach the quorum, which is the blue and the yellow lines, we can see the improvement made by the duplicate revision change. And in the case of the comparison between the pink and the green lines in the accusations that do reach the quorum, we can see that it is a bigger difference because it includes both of the improvements in efficiency, both the duplicate revision and the matching accusations, because the process of finding matching accusations is only done when the quorum has been reached. So our story does have a happy ending. We were finally able to implement a system that is secure and efficient for sexual assault reporting. It is an open source prototype that you can see in that link. So the main takeaway of this work is that distributed protocols do not need every single operation to be distributed, that it is possible to closely examine a protocol and decide where these are needed and where they are not needed so that the protocol can be much more efficient. There are still some open problems. Our work has some limitations. I did not have the time to get into it, but one of the limitations it has is that now the users have a limited number of tokens that they need to submit an accusation. So it will be interesting to see how we can change this so that they can have an unlimited amount of these tokens. And the other thing is that here the matching criteria is just a string, the string D, and it would be interesting to study more realistic matching criteria, maybe more flexible ones. So it would be really interesting to look into that. I hope you enjoyed this presentation, and I'm here if you have any questions.
Okay, I don't know if anyone can hear me. We're having some trouble here with the well, the internet went down, so
We can hear you.
I'll
Yes.
try to ask the question. I probably won't the answers, so we'll see how that goes. Okay, so the first question was for Søren. What about other blockchain systems? How would your idea work there? Did you look at that?
Right. Thanks for the question. So we actually did. So what we achieve with this giving weight to blocks instead of just length is that we get this optimistic form of optimistic responsiveness, and there what we need, what makes it optimistic is that we need that there are no adversaries around, as otherwise we can't guarantee anything. But this when one could for example add a finality layer to this solution, which means that we will be able to detect what we are already agreeing upon, and thereby sort of immediately receive this optimistic confirmation time when there are no adversaries, so that we don't need to worry about whether or not there are adversaries or not. So this combines. We imagine that this combines very well with for example, such a thing as a finality layer that is now becoming. A lot of teams are adopting this idea, and ours would work particularly well with this, as this would really increase both the throughput and the confirmation time.
Okay, Søren, can I ask a question then?
Surely.
So this weight blockchain that you present, is that like independent of how you create the block? So if it's proof of work, proof of state, or
right.
There are link that.
Right. So for this work, we have only considered the proof of work option. So we imagine that something similar could be made to work for proof of stake as well. But the thing is that the proofs are slightly different. So our proofs exploit this fact that each winning ticket or winning event in the lottery that will only be placed on a unique chain. But for proof of stakes lotteries, this is not entirely true, right? There could imagine an adversary sort of signing two different blocks, which has the same winning ticket, and thereby placing them on different winning chains. So, so right now our framework is limited to analyzing only proof of work solutions.
Cool.
Thanks. Right. So maybe I can ask a question, Elena.
Yeah.
So I understand your system correctly. Then, right now, what prevents the reporters from becoming public is that there are not enough reports, right? So until you reach a certain threshold, this is this is anonymous.
Yeah, that's the idea.
But I was wondering, this kind of assumes that all users in the systems behaves honestly, right? Those who can actually make reports. So if there were sort of potential dishonest players among those set of users, then they could reveal the other users.
Yeah, so the thing is that the identities in the system are like tied to real identities. There is a registration system, so like the system cannot really prevent false accusations from occurring because that's like outside the cryptographic protocol. That's just like human behavior. Even though like the percentages of false accusations in social reporting are really, really low, like in general, like most studies show that. So yeah, it cannot prevent false accusations, but the identities are tied to real identities. So once the quorum is reached and the identities are revealed, like the people who put these false accusations in would be contacted and like their identities would be known. So that could be like a way to prevent that in some way.
So it's not, I mean, so I was not so concerned about false accusations, right? Because as you say, but also, right, users could really make a false accusation only with the purpose of revealing who the other accusators were. And that's sort of what I'm a bit concerned about. Yeah,
but the thing is, like, the protocol does prevent accusations like that are malformed and all of those things like to be submitted. Like, so the only way to do that is to actually like make a false accusation. That would be the only way to do something like that and like tie to a real identity. So
that makes sense.
Yeah.
I do also have a question. Oh, sorry. I also have a question regarding like the model in general. I don't know if I missed it, but what is your assumption when it comes to the servers? So you said that you distribute things to the server, and then the server together can recompute the identity of an exposed persecutor in case. But do we assume that they are honest but curious or malicious? Like
no, we assume that they are honest but curious. Yes.
Yeah.
And that the majority. We assume we have a majority of honest servers. That's the thing. Yeah, and we can have a minority of malicious servers, actually, yeah.
Really? Because like I was thinking, the moment in which you upload a Elgamal ciphertext, because it's malleable, somebody can perturbate this ciphertext, and then, you know, it might end up to a different identity than the initial one. Do you have some
but because all of the servers need to agree in order to reveal or decrypt any ciphertext, like if someone would, like one is submitted, all the servers actually receive it, so they can all see what they're decrypting, and if a server would like decrypt a different thing, like the majority would see that and see like that's not the right one.
Okay. So like you assume that every ciphertext is copied to all the servers.
The ciphertexts are sent to every single server, yes. The shares are only sent like directly to each one, but the ciphertext, So.
Right. So I believe that even though Nicholas went offline, he manages to ask some questions in the chat. So I'll just read it out loud for you, Elena.
Thank you.
So Nicholas asks, which versions of pairings do you use, and does it matter for efficiency?
We do our implementation on different curves. I'm trying to find out if we have like optimal 8 pairing or whatsoever, but the curves that we use is like BN curve, BLS12, and BLS24. And in all of them, basically, we get some efficiency gain. So I think it's somehow cross curves and cross pairing. You get different gains, but efficiency gain everywhere. Yes.
Right. So Elena, just a question for me as well. I thought, so are there any examples sort of where this is used, this thing of delegating the computation of the pairing? Are there any examples of where this is actually used sort of in practice, or can be imagined to be used in practice with the new system?
Yes, thank you for the question. So used in practice, I would say not that I'm aware of, mostly because up to now there was no real efficient way of doing so. In the future, yes, like IoT devices, now they could save a lot of battery. If anyway they are communicating to a server, they can also save battery. They don't need to do certain computation on their own. But also smaller devices like AMR devices that don't have enough space to store the whole library of how to compute a pairing. Then they could outsource this computation and only do a quick check. So there are some very resource-constrained devices, like even your credit card, let's say. You don't want to store all of that thing. You don't have enough space.
Right. So this could really be imagined to be used sort of in a pay situation where you could sort of swipe your credit card and or use the chip of your credit card, and then it would outsource the computation. Or nice.
So Nicholas is writing more questions here, so I'll read it. So he asked Elena, how hard is it to get good curves?
So I think that's a question which is somehow independent of how to outsource a computation of a pairing. Like we have enough curves that we believe to be, I would say, secure from the cryptography perspective. And you usually don't want to necessarily go for a new curve every time. You want it to be well studied to say, okay, I can actually trust this one.
I have a question for you, actually.
Please.
Yeah, like how hard was it for you to actually implement a secure prototype? Because you always hear like, don't roll your own crypto. But when I was trying to do mine, I was trying like to find the curves and everything. It was actually really hard because there were like, for me, at least so many moving pieces that it was hard like to implement it securely. So how did you how hard was that for you? Did you like find some way that worked for you?
Well, we have an implementation magician, that's Diego Aranya, and he is actually using his own library, which is Relic, which is a very good library if you want to start implementing these things. So there are, very well
the curves are implemented in Relic.
Yeah. And also to answer to the previous question, yes, we did implement the optimal 8 pairing in all of the, which is the fastest pairing to date in all of the curves. So yeah.
Right. So I believe that there's a question to you, Elena, from Nicholas.
Yeah. Yes.
So he asked if there could be a user-defined accusation threshold.
Yeah, that's a very interesting question. Actually, the secure allegations escrow protocol does have that in consideration, and Who2 doesn't. We actually, before starting to design the protocol, we interviewed lots of people and did focus groups to understand what people would need in a protocol like this. And we could not have a clear conclusion on if that would be a good thing or not, because especially with sexual assault reporting, people we want to have people do it more, and with people have to select so many options and they don't know what to select, it's sometimes that can make them not want to make the accusation because it's a difficult process. So it's a question if that would be something that would be meaningful or not. In Who2 and Who2 Plus, it is not an option. Like a direct way to do it would be to have as I mentioned briefly during the talk, these are done with privacy-preserving polynomials. So you have polynomials that represent the set of accusations. So you could have different polynomials for different quorums. And then if a user wanted to have a defined quorum for each user could choose, and then you could choose in which polynomials these accusations could go. But it would be interesting, it is an open problem, to find a more efficient way to actually do that in Who2.
Building on that, so you have this master secret key at a certain point that you generate, and I guess securely you want to have it via NPC ceremony, so that you don't have a single point of trust, because anybody knowing that would break the whole system, right?
Yeah,
okay.
Yeah. So it's a secret shared key that it's generated among the servers. Yeah, all of the keys that secret keys among the servers are generated like that.
Is your implementation available somewhere? Do you know if the University of Chile is actually using it?
No, yeah, it is an open source implementation, so it is available. It is like a prototype and proof of concept. It's not ready to be used in an actual context. It's important, I feel, to say that, but it's a prototype and a proof of concept that works, and it's an open source prototype.
Okay, thank you for the clarification. Do you have any questions, Elena?
I think that's it. Yeah. Okay. Do you guys have any other questions?
Yep. Good. Then I think I will thank everybody, every speaker and everybody attending. And now it's break time until 9 a.m. Colombia time. Have a nice day. Bye.
Thanks.